Hello there and welcome back. So in the last video we briefly continued our discussion of our investigation on how to find the fractional integrals and derivatives of, elementary functions that we're pretty much familiar with in terms of powers, exponentials, and trigonometric functions. So we already proved that the Riemann-Liouville fractional integral from 0 to x of x to the nu followed this pattern, which matched our intuition, and the Riemann-Liouville fractional integral with base points negative infinity to x of e to the eta x gave us this expression that we like. But notice that the base point pretty much was chosen by us to sort of give us answers that we want, right? And we came across a problem in our investigation of sine because we used the Taylor series for sine, because then we could use this property, which already makes sense, to sort of help us choose what this base point a should be. And we showed that the RL, fractional integral of order alpha, of sine of x was equal to the sum from k is equal to 0 to infinity of negative 1 to the power of k all over gamma of 2k plus 2 plus alpha times x to the 2k plus 1 plus alpha, right? And we showed that when alpha was equal to negative 1, this gave us that the fractional integral from 0 to x of negative 1 of sine of x was equal to negative cosine of x, which is fine, but it had this plus 1 that was problematic. So in this video, we're going to investigate base points in a little bit more detail and try and see if we can figure out what a base point should be for the function sine of x. Alright, so let's formally ask the question that we want to answer here. So is there a base point A we can use for this integral operator I to match up with the alpha values that are nested inside of the natural numbers? So negative 1, negative 2, negative 3, and negative 4. Alright, so let's try and figure out maybe what would make sense for these types of things. So let's take a look at the derivative of sine and its derivative as well and see if we can sort of figure out some pattern that maybe we want, right? So this is going to be sine, right? So this is going to be y is equal to sine of x. Let's do y is equal to cosine x, and then y is equal to minus sine of x. So we know cosine of x starts off up here, and then we have negative sine of x, which is somewhere right there. So let's focus on this little point here. So one can say that this point is actually the same thing as that point, and that point is the same exact thing as that point. So pretty much what we see is that this point, this maximum, is sort of shifting over, right? It's shifting over by pi over 2 units each time, right? So this is, as we know, pi over 2. This is 0, and this is minus pi over 2, right? So if we want to go from here to here, we shifted to the left. So this is left pi over 2. This is left pi over 2. And if we want to jump from here to here directly, this is left 2 pi over 2, or just pi, right? So if we want to say the derivative of sine of x, we can just say that this is just going to be equal to the sine. So how do we say left in horizontal transformations? So that's just going to be x plus pi over 2. So we can say that the derivative, second, of sine of x is just going to be equal to the sine of x plus 2 pi over 2. And we can, of course, extend this to any integer k, right? So this is just going to be equal to the sine of x plus k pi over 2. Let's make this a little more neat. So k pi over 2, right? And this is true for any natural number k, and we can use that proved by mathematical induction. There seems to be no issue here, so one can possibly extend k in the natural numbers possibly to the set of reals, or maybe even the complex if we're feeling curious, right? So possibly one can say that the fractional derivative, or the fractional Riemann-Liouville derivative of sine of x is going to be equal to sine of x plus alpha pi over 2. And let's assume that alpha is in the set of positive reals here. And we can replace alpha with negative alpha, and we can say the Riemann-Liouville fractional integral of order alpha of sine of x is going to be equal to the sine of x minus alpha pi over 2. And of course, again, alpha is in the set of reals. So are these really what they should be? Yes, it matches up with the natural orders, but it's not necessarily the only one that matches. So do these formulas match up? So we can either use the Grunwald-Letnikov derivative to prove this, or we can use the Riemann-Liouville integral for this. But again, it will come back to the question, what is this base point A in these expressions, right? What should A be in order to give these results? Alright, so since we know the Grunwald-Letnikov derivative is typically a little bit more complex to work with, since we have, that infinite series, which also has a horizontal shift in it, with this it probably isn't going to be that much different compared to the Grunwald-Letnikov, the Riemann-Liouville fractional integral formula for sine that we've already found. But that's beside the point. We'll discuss, how to calculate via each, and maybe one is easier than the other in different circumstances, of course. So let's choose a different alpha that's not an integer and sort of investigate that. So let's consider alpha is equal to 1/2. And we're going to be working with the Riemann-Liouville fractional integral since that was what we've been working with recently. Alright, so if we use this intuitive formula that we've extended from the natural numbers, then this should just be equal to sine of x minus, so this is just 1/2, so half of pi over 2 is going to be pi over 4, right? So this is what we want. Well, question mark, is this really what we want? I mean, it matches our intuition from the natural numbers set, but maybe it's not exactly the natural thing that it should be. So let's consider the true, or the relationship that we derived with the base point 0 of sine of x. So via this relationship, we proved that this is just going to be equal to the sum from k is equal to 0 to infinity of -1 to the power of k all over gamma of 2k plus 2 plus 1/2. Now that's no longer a natural number, times x to the power of 2k plus 1 plus 1/2, right? Alright, so let's just plug in a couple numbers into this formula. I'm going to consider this what we want representation to start. So I 1/2 of sine of x, I'm going to evaluate this at x is equal to 0, right? So this is going to be equal to sine of negative pi over 4. So we know that's negative 45 degrees. Cosine of x, sine is y value, so this is going to be negative square root of 2 over 2. But if we choose the RL version, so this is going to be 0x 1/2 of sine of x at x is equal to 0. This is going to be equal to what? Do you know? This is going to be equal to 0, right? Remember, this point pretty much corresponds to the upper limit of that integral bound, right? So recall a property from integral calculus. So recall that if f of x is continuous around the point x is equal to 0, or in general x is equal to a, then one can show that the limit as x approaches a of the integral from base point a to x of order alpha of some continuous function f of x around that point is going to be equal to 0. And this is going to be true for all continuous functions around that point, right? So a continuous point around x is equal to 0. Different ways to notate that, right? So perhaps, so what does this mean? So perhaps this base point is, or is not, what we want. Again, question mark, right? All right, so what I'm going to do is I'm going to define this function, g base point a of x. I'm going to define this to be equal to 1 divided by gamma of 1/2 times the integral from a to x of x minus t to the power 1/2 minus 1 times sine of t dt. So what is this function that I'm defining? Can anyone take a guess? So if you sort of look at what this is, so this function g of a of x is what I'm defining as the RL definition, or the RL derivative of order alpha of sine of x, in particular 1/2, right? And we're trying to sort of compare it. So we're going to compare this function for various values of a to the function g of x is equal to sine of x minus pi over 4. So this function over here is what sort of is extended from the natural number case of sine, and similarly for cosine. And this is what we have proven for the general extension from the derivative from the limit definitions and the integral definitions, right? So maybe there is a relationship between these two, and maybe we can sort of vary this parameter a to sort of see, okay, maybe there is an a that will generate this, and then we can sort of investigate, does that a make any sense? So let's jump to the software and sort of investigate what this function g, capital G sub a, actually looks like. All right, so let's just jump into Desmos, since it's a pretty friendly software to sort of analyze things with. So let's call the little function g of x. So this is going to be sine of x minus pi over 4. So we're trying to figure out what base point a is actually going to generate this, right? So let's create another function g that's going to be a function of x with parameter a. So this is going to be equal to 1 divided by gamma of 1/2. Now in Desmos it uses the bad notation in terms of factorials. So this is going to be 1/2 minus 1 factorial times the integral from a, because we don't necessarily know what that a is what we want. This is going to be x minus t to the power of 1/2 minus 1 times sine of t dt, right? So let's graph g x of 0, right? So this gives us our little cosine weird looking function, right? Now notice that capital G and little g actually do share a lot of the similar points and behaviors, right? Notice that they pretty much converge as x tends to infinity, right? And that would be a good exercise for the reader if you're interested in trying. That capital G converges to little g as x tends to infinity, right? That'd be nice. So the issue is this base point. So let's actually move 0 to the left-hand side. Let's go to say, I don't know, say -5, right? So of course, if we move it to -5, it's going to go to 0, or at least try to converge to 0 at that point. But notice that the curve on the right-hand side, capital G of g, actually converge a lot sooner. So an intuitive choice or move from here is to make this even smaller, right, or more negative. So as we see, if we make this number smaller and smaller and smaller, that the discrepancy between these two curves will get smaller and smaller as well, right? But of course, not small is small enough because this error sort of perturbs throughout the entire wave, right? But one can show that as you make this closer and closer to negative infinity, these curves will actually collapse in terms of the error across the entire interval, which is pretty nice. So we've at least numerically showed, at least in Desmos, that as a tends to negative infinity from the right-hand side of this function capital G sub a of x, this actually converges to our function that actually makes sense. So it is reasonable, at least from this discussion, that maybe we should define the fractional integral of sine of x to be equal to the Riemann-Liouville fractional integral with base points negative infinity to x of alpha of sine x to be equal to sine of x plus alpha pi over 2. And similarly, one can investigate for cosine that we should define this to be equal to the integral from minus infinity to x of alpha, and this is going to be equal to cosine of x plus alpha pi over 2, right? So that gives us our fractional integrals, and similar for fractional derivatives of sine and cosine. Now, of course, this adds things to the list. For example, we've already proven this relationship. This was equal to e to the eta x over eta to the power of alpha. And remember, this was also the integral from minus infinity to x of alpha of e to the eta. So that made sense. So now here's an interesting question. So what about the fractional integral of the power? Which of course we've, proven and used a couple times, of x to the nu plus alpha, which we chose with base point 0. So how come all of these work as normal with negative infinity, but this one is special? So if we were to make this base point negative infinity, would this result here still hold? Right? So perhaps this formula is actually not even correct. Right? So in the next video in the series, we're going to investigate this particular question by investigating base points in more detail and also describing these concepts in terms of both the Grunwald-Letnikov fractional derivative and the Riemann-Liouville fractional integral. Hope you enjoyed.